myself, Roberto Percacci, and we can count on the invaluable help of Holly Hatch, who's standing over there, and who most of you, I think, have already met. Now, I will take just a couple of minutes of your time to make some introductory remarks on this meeting. First of all, I see many faces of old friends, and but I also see other people who are probably not insiders in this field, and some of you may ask yourself, what happened 30 years ago? What are the 30 years that we talk about in the title of this workshop? Now, very briefly, it so happens that Einstein was born in 1879, and in 1979, Cambridge University Press published an Einstein centenary volume. It was edited by Hawking and Israel, and it contained essays by a number of leading experts in general relativity. And among these, there was a contribution by Steven Weinberg entitled Ultraviolet Divergences in Quantum Theory of Gravity. And in this contribution to this volume, he laid down the idea, he proposed this idea that perhaps in spite of being perturbatively non-normalizable, gravity may still be well behaved in the ultraviolet and predictive, provided it satisfied certain conditions. And these conditions he called asymptotic safety. So most of us have learned of asymptotic safety from that paper, and so it came to be regarded as the beginning of this particular line of research. So it is 30 years of that paper that we are recur this year. There may be a little historical imprecision because the name asymptotic safety was used a couple of years earlier actually, in some Erice lectures. But for some reason, most of us know the Einstein centenary volume better. So conventionally, let's take that as the starting point of this line of research. Now, this research proceeded a bit slowly in the beginning, but it has taken up a lot of momentum in the last 10 years. I maintain a little bibliography on this, and I counted 12 papers on asymptotic safety up to 1998, and roughly 75 since then. So this has reached by now a certain size, and a number of us thought that the 30th anniversary of Weinberg's paper was a good excuse to have a meeting and to see where we have arrived and to discuss where we should go from here. So, to the best of my knowledge, this is the first time that the meeting is devoted entirely to asymptotic safety, and I'm pleased to say that almost all the people who have contributed to this subject will be present here. And so for those of you who want to learn about it, it's a great opportunity, I think. And we have also invited people from neighboring fields, so who don't work on this subject, but experts on related subjects, who I hope will contribute their own point of view to our proceedings, and if necessary, also their critique. So I would like at this point to take an opportunity to thank the Perimeter Institute for making this meeting possible. It's, for me personally, it is a very, very nice thing. And before we begin with the morning's activities, I just want to make a couple of logistical announcements. The first talk today takes place in this theater because we were foreseeing a larger audience, but all the rest of the activities will take place in Bob Room, which is on the 4th floor in this building, just on top of here. Lunch will be served at the Black Hole Bistro, which is straight upstairs on the 4th floor. And tonight there's a conference dinner at 6 p.m., also in the Black Hole Bistro. Last remark, well, those of you who come from outside, if you want a wireless connection, you find in your kit instructions with usernames and passwords and everything you need to connect to the internet. So after these preliminaries, if there's no questions, I think we can start with the morning's activities. And it is a great pleasure and honor to have Professor Steven Weinberg from University of Texas here with us. As I said before, he is largely responsible for our being here today. His many contributions to particle physics, quantum field theory, and cosmology are known to everybody. And so I will just add my personal hope that asymptotic safety will come to be known in the future as being as important as his other contributions to science. Thank you. Professor Weinberg will talk about prospects for asymptotic safety.
Thank you very much. I want to express my gratitude to the Perimeter Institute for hosting this meeting. And in a way that's unusual for me, I want to express my gratitude to many of you in the audience who will be giving talks in the next today and in the next few days. My work on asymptotic safety really ended in 1979, and I was busy with other things for 30 years. And only in the last 12 months has my interest revived, and it's largely, in fact, it's entirely due to the work of people who are in this room. Many of their names will be on the slides. I'm not going to try to remember their names to say them now because I'm sure I would forget someone and then I would have to apologize for it. But I am very grateful to those of you who've been working in this area for reviving this old idea and making it seem as if, well, perhaps it wasn't so silly after all. Going back to the late 1970s, it had become apparent, largely because of experience with chiral dynamics, the theory of low-energy pi mesons, it had become apparent that non-renormalizable theories were just as renormalizable as renormalizable theories, providing that you kept every possible term in the action that was allowed by the symmetries of the theory. And it was fairly clear that that would apply to gravitation as well. What you would get then would be an effective field theory that would be good for doing calculations, including quantum mechanical calculations with loop graphs at low energies. You would generate a power series expansion, not in the coupling constant, but in powers of the energy divided by whatever fundamental scale there was in the theory. In chiral dynamics, the fundamental scale was 2 pi f pi, about a GeV. In the theory of gravitation, it was doubtless something of the order of the Planck scale. With an ultraviolet cutoff, the effective action would take the form in the first equation. What I've done here is to write every term up to, well, I got tired after 6 terms, but there's a dot, 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 which means go on, include all other possible terms, an infinite number. What I've done is to take the couplings and extract whatever powers of cutoff you need to make the remaining parameter dimensionless. So, for example, G1, which is the coefficient of the Einstein-Hilbert term R, is what is conventionally called 1 over 16 pi g, and with a 1 over lambda squared, so that G1 would be dimensionless. And that's why there's a lambda square there. Now, I should say a few things about this right off before I even come to asymptotic safety. First of all, I can only show a certain number of terms, and I show them for illustrative purposes. I am not, in anything I've done in the last few months, I've not gotten to the point of doing numerical calculations. So nothing I do will depend on any particular truncation. And when I break it off and say plus dot, 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 I mean the terms I write are just there to illustrate the point, but nothing I say depends on just keeping these terms. Another point, lambda, I said, is an ultraviolet cutoff. For the purposes of this talk, lambda can either be a sharp ultraviolet cutoff, which would mean that when you calculate using I lambda as an action, you're supposed to include loop graphs cut off at an ultraviolet, cut off at a momentum of order lambda, well, let's say at a momentum equal to lambda, and that means that I lambda itself contains all loop graphs with momenta less than, with momenta greater than lambda. So lambda is an ultraviolet cutoff when you use I lambda to calculate things, but lambda is an infrared cutoff when you calculate I lambda. But it doesn't have to be a sharp cutoff. It could be the momentum parameter in a regulator term, which is usually in the literature these days called K, little k, or it could be a sliding renormalization scale in the sense of Gelman and Liu, which is usually called mu. There is one place in what I say where it will make a difference, but for most of what I say, it will not make any difference. Now, as I said, the idea of gravitation as an effective field theory was already, I don't know how widespread it was. Certainly, I regarded it as fairly well accepted. But the general attitude was that this theory was only useful as a low-energy approximation. It would inevitably break down when you carried calculations to energies of the order of the Planck scale. And this can be seen thinking of the renormalization group flow. The lambda dependence of the couplings is fixed by the condition that physics doesn't depend on lambda. And that generates a renormalization group equation that lambda d by the lambda of g of lambda is some function beta of g of lambda, one function for each coupling. Now, there is an important distinction between general relativity and flat space theories, which has been made clear in recent literature, actually going back a decade or so. And that is, in flat space theories, we make a distinction between essential and inessential couplings. The essential couplings are those which are not affected by a redefinition of the fields. The inessential couplings, like renormalization constants of fields, are so affected. And the important difference is that the essential couplings form an invariant surface in coupling constant space. The logarithmic derivative of g of lambda is a function just of g of lambda, whereas for the inessential couplings, their beta functions depend on themselves, but also on the g of lambdas. We don't make that distinction in the quantum theory of gravity because the cutoff inevitably depends on the metric. That's a requirement of general covariance. And because of that, the kind of field redefinitions that we would use to explain this distinction between essential and inessential it produces complications due to the fact that you also have to change the cutoff. And so I will not be making that distinction. Now, the idea of asymptotic safety is, of course, that the theory is safe from couplings blowing up as lambda increases if the beta function has a zero, I call it G sub star, and if the coupling is on a trajectory attracted to G star. The surface of all the couplings that are attracted to G star when the cutoff goes to infinity form what's called the ultraviolet critical surface. And there's a physical requirement that the actual couplings lie on the ultraviolet critical surface, and that should be regarded in the same sense as the old requirement in, say, quantum electrodynamics that the theory be renormalizable. It's a requirement we impose to avoid problems at very high energies. The number of free parameters, once we make that requirement in the theory, equals the dimensionality of the ultraviolet critical surface. Way back in '79, I pointed out that even though you have an infinite number of couplings, you can very well expect to have a finite dimensional critical surface, which might seem surprising at first. There are two hand-waving arguments for this. One is an argument based on continuity. If you start with a theory that has a Gaussian fixed point, that is a fixed point corresponding to a free field theory, and with a free field theory, furthermore, which is asymptotically free, like quantum chromodynamics, and then you do something like increase the dimensionality or change the number of fields to make the fixed point move away from zero, you wouldn't expect the zero of the beta function just to disappear suddenly. You would expect, at least for some range of parameters, there would still be a zero of the beta function within some regime around the origin. And furthermore, if at the Gaussian fixed point, there is a renormalizable theory, that means there are a finite number of ultraviolet attractive directions that are attracted into the fixed point as the cutoff goes to infinity. Well, as you go away from the Gaussian fixed point, you would expect perhaps some ultraviolet attractive directions to become repulsive or vice versa, but you wouldn't expect that to happen to an infinite number of directions. So although the dimensionality of the ultraviolet critical surface can change, and in fact we know cases where it does change, you wouldn't expect it suddenly to blow up and be infinite. That's a theoretical hand-waving argument. The experimental hand-waving argument is simply the existence of second-order phase transitions in nature. We learned from the work of Kenneth Wilson that a second-order phase transition corresponds to an effective field theory in which there is a single infrared repulsive direction. And it doesn't take a lot of thinking to realize that a single infrared repulsive direction is also a single infrared ultraviolet attractive direction. And so second-order phase transitions correspond to effective field theories with one-dimensional ultraviolet critical surfaces. Although, of course, as you approach the fixed point in the theory of critical phenomena, the effective field theory breaks down. The hope with asymptotic safety is that the theory does not break down and that you go all the way to the fixed point, remaining in the same theory with the same degrees of freedom, the metric and whatever matter fields you have. Now, those hand-waving arguments needed to be buttressed by actual field theoretic calculations. The first ones were done using dimensional continuation from two dimensions where general relativity is renormalizable but trivial to 2 plus epsilon dimensions where you have a non-Gaussian fixed point at a distant epsilon from the free field theory, and then crossing your fingers and extending epsilon to the value 2. Sorry. I seem to be in a closed loop. Maybe I can do it with this. Yes, that works. The 1 over n expansion was used to get similar results by Smolin, and then much more recently by Percacci. Lattice quantization has been applied by a group in Copenhagen, but this thing just doesn't work. But the big breakthrough, I think, was the application of the truncated exact renormalization group methods, which had been developed in the theory of condensed matter by Wegener and Houghton originally, and then applied in quantum field theory by Polchinski and Wetterick to this problem, initially by Reuter. The idea is, although the exact renormalization group equations link all couplings, you truncate the equations by setting all but a finite number of the couplings equal to 0, and you just have to ignore the fact that the beta function for some of the couplings you're setting equal to 0 turns out not to be 0, so that you're not really solving the equations. But you hope that if you include more and more terms in the truncation, that it'll work out all right. A large number of authors following Reuter's original work included more and more terms in the truncation, some of them including matter. And I've given a list here. I think I'll let you read the list. It goes on the next slide. And I think all of the people who worked in this are in this room. And I'm not telling you anything you don't know. Now, for a while, I knew vaguely about this, but at first I was not very much encouraged by it. And the reason was that in all of this work, there were either two coupling parameters, in which case the authors found that the critical surface was two-dimensional, or three parameters, for example, r to the 0, r to the first, and r to the second, in which case the authors found that the ultraviolet critical surface was three-dimensional. Now, I thought that if this continued, we would be out of luck, because if every time you added more parameters, the ultraviolet critical surface got higher dimensional, you would wind up with an infinite number of free parameters. And even if, in some sense, this theory was ultraviolet complete, it wouldn't be very useful. The thing that got me enthusiastic again in just the last 12 months is work by Codello, Percacci, and Ramadi, and Benedetti, Machado, and Sauresig, who considered truncations with more than three coupling parameters, and in the first case, with up to 9 coupling parameters. Capital N is the number of coupling parameters. And they found, I'm sorry, that statement, n greater than 3 ultraviolet attraction, that's wrong. They had n greater than 3 coupling parameters, and yet they found in all cases that there were just 3 attractive directions. In other words, the ultraviolet critical surface was just three-dimensional. And it didn't matter whether you had 4, 5, 6, 7, 8, or 9 free parameters in your truncation. The ultraviolet critical surface was three-dimensional. I found that very encouraging. It suggested that perhaps we are, and in some cases matter was included, although so far I believe only free matter, that is matter without its own self-interaction. But I found it very encouraging. It was the beginning of a suggestion that perhaps these theories are theories which are ultraviolet complete and have just 3 free parameters, one of which would be a scale factor that tells you where you are on the trajectory heading to the fixed point, and the other 2 would be dimensionless parameters that tell you which trajectory you're on. Now, whoops, I jumped ahead too far. Somehow I managed to jump ahead to the end of the talk. Now, there are problems. Let me make sure I didn't skip them. Yeah, that's right. There are problems. And I think we're all aware of these problems. One problem is, the most obvious one, does the sequence of truncations actually converge? We don't have any mathematical theorems. There's no functional analysis here, like there is in simple scattering theory, that guarantees that as you include more and more terms in a matrix representation of the scattering kernel, you approach the right answer. We don't have anything like that here. All we have are numerical experiments. They are moderately encouraging. Here, I list the results of the two papers I mentioned before. The most obvious test is for the eigenvalues in the renormalization group equation, the eigenvalues of the matrix of the derivatives of the beta function with respect to the coupling constants. These eigenvalues tell you the behavior of the couplings as you approach the fixed point. They are invariant to the definition of the couplings. And that's why it's convenient. And they're also invariant to whether you're talking about an ultraviolet cutoff or a sliding renormalization scale. The eigenvalues are the same. And so it's convenient to think of them as a test of the truncation. And as I said, in these models, there are three attractive directions. The eigenvalues can come in complex conjugate pairs or be real. So the condition for being attracted in the ultraviolet to the fixed point is that the real part of the eigenvalue be negative, and at least in the notation I use. And these are the three ultraviolet attractive eigenvalues found in the cases considered by these authors. And as you see, the complex ones sort of converge to a definite value, about -2.5, plus or minus about 2.5 times I. The real one is a little bit more jumpy, jumps around, and in fact, Benedetto, Machado, and Sauressa get a value which is quite different from Codello, Percacci, and Ramadi, although they only have 4 terms in their truncation. And Codello, Percacci, and Ramadi also got a result which only settled down after you got more than 4 terms. So, so far I find this moderately encouraging, but a lot more needs to be done. The second problem is a more fundamental problem. Is asymptotic safety really necessary? Now, my intuitive feeling, and I think most of you share it, is that if the coupling constants don't hit an ultraviolet fixed point as lambda goes to infinity, you're in trouble. They may blow up at some finite energy, for example, as you have in, as Landau suggested in quantum electrodynamics. Or something bad will happen. And at any rate, it is pretty clear that if the couplings do approach a fixed point as lambda goes to infinity, the theory will be well behaved and something we can hope to calculate with. But do we really know that that's necessary? What is needed is to study theories that are not asymptotically free and show that, in fact, something really does go wrong as lambda increases. Now, thinking about this, I realize that what goes wrong depends, and this is the one place where it does matter whether you're talking about an ultraviolet cutoff, whether a sharp cutoff or a parameter in a regulator function, or you're talking about a sliding renormalization scale. If you're talking about an ultraviolet cutoff or a parameter in a regulator term, then certainly all observables must approach finite definite limits as lambda goes to infinity. Because lambda going to infinity means you're going to the real world where there isn't a cutoff. And so things have to have it's like going to the continuum limit in lattice calculations. That's the real world, the continuum. So things have to have a finite definite limit. But the couplings, which are functions of lambda, these coefficients of terms in the action that I showed in the first slide, they're not physically observable parameters directly. They're not directly observable. And it isn't clear that, that they have to approach a finite definite limit. Observables must, but they are themselves not observables. So there's a weak point in the argument here. On the other hand, if lambda is a sliding renormalization scale in energy at which things are actually measured, like, for example, the energy at which the electric charge is measured in the original paper of Gelman and Lowe, then it is true that and if the couplings are defined as observable quantities, like the electric charge in quantum electrodynamics, then they must not do something weird like blow up at a finite value of lambda. But it isn't clear that they have to approach finite definite limits as lambda goes to infinity. Even in the case where you have a simple coupling, a single coupling, the relation between g of lambda and lambda is given by that equation. Whoops. By this equation. I can't point. Well, there's only one equation there, so you see it, the one in blue. It's given by that equation. And if beta of g is positive for finite positive g, then certainly if that integral converges in other words, if beta increases as g increases rapidly enough so that the integral converges as g goes to infinity, then g will go to infinity at a finite value of lambda given by that integral. And if g of lambda is observable, you're really in trouble. But there are other possibilities. Beta of g may go to infinity, but sufficiently slowly so that the integral doesn't converge. Like beta g could go like g to the alpha for alpha less than 1, in which case g of lambda goes to infinity for lambda going to infinity. But even if g is an observable quantity, it isn't necessarily unphysical for an observable quantity to become infinite when the energy becomes infinite. Where is it written that all observable quantities remain finite when the energy becomes infinite? And with more than one coupling constant, there are many other possibilities, like limit cycles, where the couplings neither blow up at a finite energy nor go to infinity at infinite energy, but just go round in a cycle, approach a cycle in which they endlessly go round. We don't know that that is not the case, and it would really be nice if we could convince ourselves that asymptotic safety is the only alternative. My intuitive feeling is that it is the only alternative, but we haven't shown that. Then there is a very practical problem. How do we deal with the radiative corrections? How do we choose and that's closely related to the question, how do we choose the cutoff? The reason they're related is that observable quantities must be independent of the cutoff. But very often when you do calculations ignoring radiative corrections, you find, and I'll show you an example, you find they're not in the tree approximation, which means that radiative corrections cannot be neglected. What one can try to do is to choose lambda so that radiative corrections are as small as possible. But you can't go too far in that direction. We have a hard choice. Consider a physical problem with a characteristic energy E, like graviton scattering at energy E. We might consider taking lambda to be much less than E. In that case, loop diagrams become negligible because E provides a natural infrared cutoff to the theory so that you get no contribution from when you use gamma lambda in loop diagrams with a cutoff less than the energy that you're working at. The trouble is that the action, as we saw in the first view graph, excuse me, the first slide, is a sum of terms with increasing negative powers of lambda, and a term in the action proportional to lambda to the minus alpha gives a contribution of physical quantities containing a factor energy over lambda to the alpha. And if we take lambda much less than the energy, then the truncation becomes pretty much useless. So we don't want to take lambda much less than the energy, even though it solves the problem of dealing with radiative corrections. Another choice, we might take lambda much greater than the energy. Then the truncation might be expected to work quite nicely. We could at least hope so. But then there's no reason for imagining that radiative corrections are small. And in fact, I'll show you examples where it turns out that physical quantities depend very strongly on lambda, so that we know that radiative corrections must be important, since the physical result cannot depend on lambda. A compromise, which I think we're driven to, is you take lambda of the order of the energy, where the truncation may be beginning to work pretty well, and the radiative corrections may be beginning to be not too large. What you need is then some technique for choosing the right value of lambda. In quantum chromodynamics, where the dependence on lambda is logarithmic, it's not very important. You choose lambda to be of the order of the energy. We all know, for example, that when you want to study high energy physics at an energy of the order of 100 GeV, and you include electromagnetic radiative corrections, you use the value of the fine structure constant at 100 GeV, and you don't have to worry about whether it's 150 GeV or 50 GeV. It isn't very sensitive. Here, however, where things depend on powers of lambda, things are quite sensitive to which particular value of lambda you use, and it's important to identify an optimal lambda. Well, those are the problems I see. Now, I would like to discuss them in my remaining time in the context where it seems most natural to apply the idea of asymptotic safety, that is, to gravitation at very high energies and short distances. And since I've been working in cosmology for the last couple of decades, I naturally think of the early universe, the theory of inflation. This has already been studied by Bonanno and Reuter, and by Reuter and Sauer-Essig. They use a severe truncation, only including, unless there are things I haven't seen, G0 and G1. They do put in matter, but it's matter not described by an action, but just defined to have a constant equation of state parameter W. And they suggest using a time-varying cutoff, which creates lots of complications that they deal with. In the work that I've done, just to distinguish what I've been doing lately from what they've done, since I'm not using any truncation of the action, but of course, that's simply because I'm not yet doing any numerical calculations, so it's easy for me to consider a completely general action. I haven't included matter yet. I don't think that what I'm doing is really dependent on ignoring matter. And I'm only considering a constant cutoff because I want to avoid the complications that come from a time-varying cutoff. As I have said several times, I'm not doing numerical calculations. The purpose of what I've done so far is to just lay out the outlines of what kind of calculations one should consider doing. Now, the first step is to consider the Robertson-Walker solution of the gravitational field equations, and I'm considering only a flat space Robertson-Walker metric. The action then, if you plug the Robertson-Walker metric into the general action, you get a factor of the spatial volume V. It's convenient to take out a factor of lambda to the fourth, and then a time integral of a cube of t, which comes from the determinant of the metric, times a function which is only a function of things which are independent of the scale of a of t, the Robertson-Walker scale factor, and hence depend on h of t, the expansion rate, and its time derivatives. Now, in general, you have 10 field equations. The statement that the action, these are classical field equations, the statement that the action is stationary with respect to arbitrary variations of g mu nu. With the kind of very complicated action we're talking about, it would really be difficult to write those down and then specialize to the Robertson-Walker case. But fortunately, you can use the symmetries of the Robertson-Walker metric to write the field equations as a single field equation. It is just the time-time component of the general Einstein equations, and it takes the form I show here. The other Einstein equations, because of the Bianchi identities, just follow from this one being satisfied. That's something that's quite familiar from the usual case where you only have the Einstein-Hilbert term and perhaps a cosmological constant. We all know then that in the Friedmann model, there's only a single equation that gives you the Hubble constant in terms of, say, the cosmological constant or whatever matter density you include. The fact that there's only a single equation is completely general and just follows from the generalized Bianchi identities and does not depend on any particular form of the action, just on the fact that it's generally covariant. And that is the equation in complete generality. I should explain what the ... means here. ... represents any contribution that comes if the function in the integrand, the f sub lambda, depends on higher derivatives of the expansion parameter h. Now, in a quite general case where, well, it's not completely general, where the action only depends on the Riemann-Christoffel curvature tensor and not on derivatives of the Riemann-Christoffel curvature tensor, but that includes arbitrary functions of r and r mu nu. In that case, there is no dependence on second time derivatives of h, and this equation without the ... is completely general. It's only in the case where you include derivatives of the Riemann-Christoffel curvature tensor in the action that you really do have to include the ... The things I'm going to say won't depend on not including them. I just include these terms, as I said before, for illustration. Now, remembering what the action is, that's the action that I showed you in the first slide. You then can calculate the function n lambda by figuring out what r and r mu nu are for the Robertson-Walker metric and taking a variation with respect to g0. Well, it's complicated, but this is the answer. And again, the ... means the same thing. This is all there is if the, no, I'm sorry, here it means something else. Here the ... means this is all there is if that's the action without any additional terms. Of course, in general, there are additional terms. And so this is just illustrative. It's quite easy to get this, actually. Now, you can now look for de Sitter solutions. That's quite easy. De Sitter solutions, A expands like e to the h bar t, where h bar is a constant. In that case, the field equation just reduces to the statement that n lambda vanishes when you set h of t equal to the constant h bar, and that gives you the field equation 0 equal minus g0 of lambda, etc. Now, here is where you have to make the hard choice that I mentioned. If you take lambda much less than h bar here is the characteristic energy, then radiative corrections are small, but the series diverges badly. You've got h bar over lambda the sixth, and so on. I don't know that it diverges, but it certainly doesn't look promising. On the other hand, if you take lambda much greater than h bar, then the series may converge. At least it's a reasonable hope. It may be dominated by its low terms, but radiative corrections are surely important, as shown by the fact that lambda, that h bar that you get by solving this equation will depend strongly on lambda. And in particular, in the special case where lambda is so large that the couplings are near the fixed point, the root of the equation clearly is that h bar is some numerical constant times lambda. And that's very dependent on lambda. So you have to try to figure out an optimal lambda. Now, as I said before, I'm going to choose lambda to be of order h bar, but I will take it at a local minimum of the radiative corrections to h bar. Now, the true expansion rate, h true, is h bar of lambda, which I got from solving the classical equations, plus a correction, which is undoubtedly quite large, delta h, which comes from the quantum corrections to the gravitational field equations. I will choose the optimal cutoff. Of course, what I really should do is set down and calculate loop diagrams and figure out what delta H is. But time is short, so instead I choose an optimal cutoff to make delta H of lambda a minimum with respect to lambda. So I set the derivative with respect to lambda equal to 0. Now, at this point, to forestall people yelling at me from the audience, I don't know whether it's a minimum or a maximum. I have to flip a coin. I'm hoping it's a minimum. Also, more important, at least I have a 50% chance of being right about that. But more important, I don't know if it really makes it small just because it's a minimum. But that's the best I can do without actually doing hard work. Now, H true is independent of lambda. So at the optimal cutoff, if delta H is independent of lambda, so is H bar at that value of lambda. Now, the field equation says that n sub lambda, the function which has an explicit lambda dependence, as a function of H bar of lambda is 0. And that's true for all lambda. Whatever lambda I choose, H bar of lambda is the solution of the classical field equations that I get. So, but at the optimal cutoff, H bar of lambda is stationary in lambda. So that means that the function n sub lambda, its intrinsic lambda dependence vanishes at the optimal cutoff. And that I can use to get a second equation. The top equation is the gravitational field equation I got before by setting n lambda equals 0. The second equation is the equation I get by saying the derivative of n lambda with respect to lambda is 0 before I put h bar equal to h bar of lambda. And that gives me this equation. I get two kinds of terms. The first set of terms, which end with a dot, 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 comes from the explicit lambda dependence from those powers of h bar over lambda. The second set of terms come from the running of the couplings. So I have something, well, this is what I get. And now I have two equations for two unknowns, and it's not unreasonable that I could expect to find a solution, maybe more than one. The solution for both h bar and lambda you would expect to be of the order of the only dimensional parameter in the theory. The only dimensional parameter in the theory, I call it capital M, sets the scale at which the couplings are just beginning to approach their fixed point. That's the only mass in the theory. Everything else is dimensionless. Now, so you expect that the result will be somewhere approaching the fixed point, but it couldn't be very close to the fixed point. That would be not to be expected. And in fact, you can show you can't be very close to the fixed point. I won't give that argument. But in the neighborhood of the fixed point, the couplings are given by the well-known solution of the renormalization group equation, where UIN is an eigenvector, and lambda I is the corresponding eigenvalue of a matrix BNM, and BNM is just the matrix of the partial derivatives of the metric with respect to the couplings. Now, capital M is inserted just to make the U's dimensionless. I can choose capital M any way I like, and what I'll do is I'll define M so that the largest U's are of order 1. The largest components are of order 1, in which case M is the scale at which the couplings are just beginning to approach the fixed point. That gives a meaning to capital M. And the free parameters are capital M and the relative normalization of the eigenvectors. Each eigenvector's direction is fixed by the eigenvector equation, by the eigenvalue equation, but its normalization is a free physical parameter. And the free physical parameters of the theory are M and the relative normalizations. And I'm choosing the overall normalization in some way so that the largest component is of order 1. Now, let me go back. Now, so far, I've only considered a pretty uninteresting cosmological solution, the de Sitter solution. That's, of course, not what corresponds to reality. We think there was a period of inflation in which the universe expanded more or less exponentially, but it had to come to an end. And the de Sitter solution, of course, never comes to an end. So what we have to do is look for solutions of the Robertson-Walker metric, for the Robertson-Walker metric, which are close to de Sitter for a long time, for many E-foldings, but then eventually move away from de Sitter. The way I approach this is to look for solutions which are just perturbations of de Sitter. In other words, H of t, which is A dot of t over A of t, is the constant H bar, which satisfies the equations for the de Sitter metric, plus a perturbation delta H of t. And I just carry calculations to first order in the perturbation. Then you get a very simple field equation, which is just a power series. First term involves delta H, the next delta H dot. I don't know if you can see the dots. And then the next term, delta H double dot, and so on. This equation, by the way, terminates with the terms that I've shown here if the action only depends on the Riemann-Christoffel curvature tensor, because then the field equations only involve H and H dot and H double dot, and there are no higher derivatives of H in the field equations, and then this is the complete field equation for the perturbations of the de Sitter metric. And the coefficients of C0 you can calculate from what was on the previous slides, and of course you get these series with plus dot dot dot. Here the dot 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 really means plus terms that come from terms that were not included in the action not included in the action at the top of this slide. But the fact that the equation may involve only second time derivatives is more general. Now, you can solve the equation very easily. The solution is just an exponential in time, where it's convenient to factor out an h bar in the rate, and so you have a numerical constant c times h bar is the rate of growth of the perturbation. C is given by an equation which in the simplest case is just a quadratic equation. And yeah, there I say it, that all Cn with n greater than or equal to 3 would vanish if the action only depended on the Riemann-Christoffel curvature tensor and not its derivatives. Now, for C less than 0, you're out of luck, because that means that the de Sitter mode is stable and you never get out of the de Sitter mode. But again, we flip the coin and hope that C turns out positive, in which case it's unstable. The number of E foldings will be of the order of 1 over C. It will be very close to 1 over C unless the coefficient of the exponential is very, very different from 1. And if, or very different from h bar. And if C0, and now you can see that if C0 is much less than 1, that's the condition that gives you a large number of E foldings. Because in that case, if C0 is much less than 1, and I should add, if all the others are of order 1, they're all dimensionless, and you expect them all to be of order 1, but if it turns out that C0 is anomalously small, then you get a number of E foldings, which is of the order of C1 over C0, which you hope is much larger than 1. Now, under what conditions would C0 be anomalously small? Well, let's go back and look at C0. Whoops. There it is. It's shown there. It's the first blue equation. It doesn't look very promising, but you have to remember the equation that and gives you an optimal cutoff. The equation that gives you an optimal cutoff is the second blue equation here. And according to that equation, the first terms, which is just the formula for Z0, just balances the second set of terms, which involve the beta function. In other words, at the optimal cutoff, C0 is just a linear combination, well, it's an infinite sum of beta functions. And so you can imagine two circumstances in which C0 is anomalously small and you do get a large number of E foldings of inflation before the instability takes over and you wind up with and you end inflation. The first circumstance is that although I said G of lambda can't be very close to the cutoff, it could be pretty close to the cutoff. And I mean, there is a limit to how close it can get, but it could be fairly close to the cutoff, in which case all the betas are close to 0. That's the simplest thing. The other argument is even if you're not very close to the cutoff, C0 will be because it just involves beta functions, it will be a sensitive function of the free parameters in the theory. And in fact, within the range of validity of this approximation, it will be a linear function of the free parameters of the theory. And it's certainly possible to choose values of these parameters which make C0 as small as you like without getting arbitrarily close to the did I say cutoff? I meant fixed point. I think I've said the word cutoff several times when I meant to say fixed point. You can't get arbitrarily close to the fixed point, but even without that, the parameters could be adjusted to make C0 as small as you like. And this could happen in a chaotic inflationary theory through anthropic arguments. Freivogel, Klebon, Martinez, and Susskind a few years ago argued that in order for galaxies to form, the curvature, the spatial curvature of the Robertson-Walker metric must not dominate the Friedmann equation at the time galaxies form, because otherwise there would be too rapid an expansion and they wouldn't form. It's very much like the old argument about the cosmological constant. The vacuum energy can't dominate the Friedmann equation at the time of galaxy formation. Now, at the very beginning of inflationary theory, Guth pointed out that one of the merits of the theory of inflation is that it explains why the curvature does not dominate the Friedman equation at the present time, which we know experimentally. And he concluded that in order to account for that, you need 60 to 70 E-foldings of inflation. Now, there's no particular anthropic reason why the curvature should not dominate at the present time when the matter density has decreased to much less than it was at the time the typical galaxies were forming. But the condition that the curvature did not dominate the Friedman equation at the time the typical galaxies were forming is almost as restrictive. And again, following Freevogel et al., and there is, if you believe in the multiverse, which you're welcome not to, but if you believe in the multiverse, then there's a strong anthropic argument that you need 60 or so E-foldings in order to create a universe which is big enough and then expands at a stately enough pace so that galaxies can form and life can arise. So it is possible either that you have solutions, inflationary solutions, which come to an end after many E-foldings, if, because of some numerical accident, the couplings turn out at the optimal cutoff to be close to the fixed point, I've said it right this time, or if anthropic considerations require a sufficient cancellation among the constants appearing in C0, the top blue equation, so that there's a near cancellation and C0 is anomalously small. Well, there's a tremendous amount of work left to be done on all these things. I mentioned at the beginning some fundamental problems which need to be addressed, and unless someone gets very clever and starts to prove theorems, these problems will have to be addressed through the kind of heroic computer calculations which some of you in the audience have been doing. And there is also the application to cosmology, which is what I've been working on, in which clearly one would want to include, at the very least, one would want to include matter in the calculations and see whether that does make a difference. And a large calculation, which is, I've not yet seen any tricks for really getting involved in terrible complexity, is to consider the theory of the perturbations to this inflationary theory, which are not just perturbations that change A of t, but actually give you the kind of perturbations that are observed in the microwave background. The simplest case would be to look at the tensor perturbations. It turns out that even in the theory of ordinary inflation with multiple scalar fields, the tensor perturbations are quite simple, and you can calculate the expected amplitude of the tensor perturbations at the present time or at the time of recombination, just knowing the history of the Hubble expansion rate at around the time the perturbations left the horizon. I don't know that that's true here, and it would be an interesting question to see whether it is. The scalar perturbations would be yet another order of magnitude more difficult to deal with. What I find most encouraging is the sight of people in the audience who are actually working on these things after all these years. Thank you. I'd be glad to take questions if there's time. But please, I'd rather get them here. Yes.
Which puzzles me. You know, there is something called the theory of renormalization of composite operators.
Yeah.
Okay, now this tells us that when you insert a composite operator, which is any polynomial of higher degrees you can consider, for large cutoffs, the leading contribution just renormalize the coefficient of operators of lower dimension. And when you have taken this into account, what remains is something which truly decays with the cutoff. So now, I didn't look into the gravitational case, but I believe it must not be that different. And therefore, most of this correction you can just put in a renormalization of the coefficient of the terms which have lower degree, like the Einstein-Hilbert action, the cosmological constant first, and so on.
Well, I believe I'm not sure, you're more of an expert on this than I am. I believe that what you say is true if you use minimal subtraction. It doesn't depend on the minimal subtraction? Well, all right, then that doesn't make the beta functions trivial, though. If the beta function for the, I mean, say if you use 9 terms in the truncation, I'm not sure the implication of what you're saying. Are you suggesting that this makes the beta functions trivial for some of the low couplings? It doesn't, does it?
Find an optimal value for the cutoff.
Yeah.
Based on the fact that radiative correction were important. But what I'm saying is that the leading part of the radiative correction are just renormalization of the term which come before in the expansion. And therefore, you don't have to worry about that.
Well, I'm talking about the radiative corrections to H bar that you calculate, which includes all of the couplings.
Yeah, but what I'm saying is that the first thing is that you can drag these terms as just simple renormalization of the coefficient of operator of lower dimensions. You see, and therefore it makes a difference.
Well, I don't see it. I'm sorry. We'll talk about it. I don't follow your point, and I'm just being stupid, perhaps, and I'm not getting the point.
I was very interested that, contrary to what you've always said, is that if you have one good argument, then that's the one that's your argument. And when you start having more than one, you should become suspicious. That's something you've always told us.
That's what Mark originally did to T.D. Lee, actually.
But anyway, I see you have the beta functions being 0, but then you say or otherwise C0 is a linear combination of.
Yeah.
Now, which of these is your good argument? I guess that's the question.
Well, I think it's the anthropic one. The other argument, you really would rely on a numerical accident, which would not be anthropically required. The point is, let me explain why you can't get too close to the fixed point. Suppose you imagine that H bar, the solution you get for the expansion rate, was very close to the fixed point. So let's call m the mass at which you just begin to approach the fixed point. H bar is much, much larger than m. Then you could choose lambda to be much larger than m, but much less than h bar. Now, if lambda is much less than h bar, then you know that radiative corrections are small. But also, if lambda is much larger than m, you know that the couplings are very close to their fixed point. Now, in that case, you can actually show, as in fact I said, that h bar is proportional to lambda, which means the radiative corrections must be large. So you get into a contradiction. So you really get into a logical contradiction if you imagine that h bar is extremely close to the couplings at h bar are extremely close to the fixed point. It's not a quantitative argument, so it leaves open the possibility, well, they're not very close, but they're sort of close. But I find that weak. I prefer the anthropic argument. But you're quite right. Since I'm giving two arguments, it means I don't know what the right answer is. Another question? Yes, there's one up there.
Okay, so if you take your sort of effective Friedmann equation you're deriving here with if you take a finite number of terms,
yeah,
because you've got high derivatives of H, you inevitably expect very unstable solutions in that equation, just by the normal Ostrogatsky kind of instability argument.
Well, if you cut it off at any finite number of derivatives, you may or may not. I mean, it might be that all the roots are negative except for one, which is small and positive. You don't know that they're. I mean, even if you cut it off as a quadratic equation, you know there are two roots. But I've looked at it to see if there are any theorems that tell you anything about the signs, and there aren't. They may both be stable. One may be stable and the other may be unstable. They may both be unstable. I can find parameters which make any one of those three possibilities happen.
But, I mean, typically you do expect with a finite number of terms, you will have
No, if you have a lot of terms, then the odds are some of them are unstable. But you may be misled by having a lot of terms and cutting it off. I mean, after all, if you look at the equation 1 minus e to the minus x, if you cut off that power series for e to the minus x at any given place, it looks like there are lots and lots of solutions. But in fact, that equation has only one solution, x equals 0. When you sum a series to all orders, many of the solutions that you see when you cut it off disappear, as shown in that trivial example.
So I guess a related question is, so I guess what I'm worried about is ghosts, because typically if you just took in the action of function of h and h dot,
Yeah.
then you get an extra scalar mode, which is sort of what you're using for your effective inflation, but usually that ends up being a ghost because you have truncated. And so my other question is also,
well, there is a ghost that has been widely worried about in the literature for many years. If you include R square terms in the action, is that what you're talking about?
Basically.
Yeah, you get a ghost, but you only get the ghost if you believe the theory up to energies of the order of the Planck scale. In fact, there's no reason to believe a simple tree approximation up to those energies. And in fact, in one of the papers, and please correct me if I'm wrong by, make sure I got the names right. One of the papers by Benedetti, Machado, and Sauer-Essig, I believe they actually use the renormalization group flow to look for the ghost, and they don't find a ghost, even though there are R square terms in the action. They considered a truncation where you have R to the 0, R to the 1, R square, and C square, where C is the Weil tensor. And they looked for a ghost and didn't find it.
Okay. Yeah, so that was my other question was, how is it, it's not obvious in this framework that, I mean, unitarity is not obvious. I guess that's the point.
Well, I've always taken the attitude that the absence of unitarity is not obvious. I mean, I've never been impressed by this ghost that you get with R squared, because it was always clear that the ghost would only occur at energies where the calculation breaks down.
So that's right, but the problem is with what you're doing is you're, in these series you've got functions of h over lambda, and I expect when you have at least if you truncate with a finite number of derivatives, you are at the scale in which you're going to
there's a real,
see that.
I think the point is not that truncation produces ghosts or produces instabilities. I think the point is that we have to learn how to truncate and not worry about the ghosts. I mean, and look at only the solutions which will survive when we take away the truncation. I mean, that's the sort of thing that's done in this test of the robustness of the calculations as you increase the truncation. As you increase the truncation, you always get new dimensions. You get new couplings. So you get new eigenvalues of the matrix B sub nm. Obviously, a new eigenvalue that just appears when you include r to the 9th, you don't worry about the fact that it wasn't there before. It couldn't have been. What you do is you look at the lower eigenvalues, the ones that are actually correspond to ultraviolet stable directions. And you see that those don't vary rapidly, and they don't. But there's a certain art in this, which we have to master, of picking out in the truncation the things that are likely to be robust against further improvements in the truncation. As the example I gave you of 1 minus e to the minus x, well, it's not obvious that, you know, even in the linear approximation to e to the minus x, there's a solution x equals 0 that makes 1 minus e to the minus x equals 0. All the other solutions you get, you have to throw away. How would you know you had to throw them away? I don't know. It depends. What we need are theorems. And there are no theorems here. There's just numerical experiments. Lee?
Just to follow up on that question, because I am one of the people who worries about ghosts, is the following a fair summary of your point of view about this method? If we assume that there is a well-defined physical theory corresponding to quantum gravity, and we want to study that theory, whatever it is, in an effective field theory language, then asymptotic safety is a good method to use, and the improved renormalization group with truncation is a good thing to do. And then it's good advice not to worry about the ghosts, et cetera, because behind you have confidence that there's a good theory.
Well, no, that's not fair. I mean, within this framework, you can see there are no ghosts. Because you can calculate where the fixed point is, true approximately. You can calculate how you approach the fixed point, true approximately. And in that region, you can see that there are no ghosts, that the couplings arrange themselves so that you don't have a ghost. It's not just that you find a ghost and hope it will go away. You don't find a ghost.
So the result of Dario and collaborators is then very crucial.
Yeah, I think so. I think so. Well, that's why I'm here. The work that's been done, well, starting with Reuter in 1998, which I didn't pay much attention to, as I said, because I was worried that the ultraviolet critical surface would just get bigger and bigger. And then in the last year, the discovery that it doesn't get bigger and bigger, it stays three-dimensional. I think this is what's exciting about the whole business.
Yes, I have a question about the beta function, the linear.
About which?
The beta function you showed before. The eigenvalues you have chosen are the real one, or you took the complex?
Well, BNM is a real but not symmetric matrix. So it is the derivative of beta n with respect to GM at the fixed point. So if you have a real but not symmetric matrix, you know its eigenvalues will either be real or will come in complex conjugate pairs. Complex conjugate pairs that's no problem. It doesn't matter if the coupling goes like this, as long as it gets attracted to the fixed point. And the condition for that is that the real part be negative. And so it's either real negative eigenvalues or complex eigenvalues with real negative real parts. What they actually find are one pair of complex conjugate eigenvalues with negative real part plus a single real eigenvalue with negative real part. And then lots and lots of other eigenvalues with positive real parts, some complex, some real. It took me a long time to make this realization that there's no particular reason the eigenvalues have to be real. And I gave this talk in, not this talk, but a similar talk in, where was it? I think Santa Cruz. And I think some people in the audience had to swallow over that. But there's no reason the eigenvalues should be real. Okay, well, I'm done.